Welcome everyone to another SIP seminar on this wonderful November 4th. And today's speaker is Professor Usman Khan from Tufts University. He's going to talk about distributed machine learning, optimal algorithms for distributed stochastic non-convex optimization. Usman is I and he go way back. He's an old friend and a wonderful researcher in he has been working in the area of distributed processing and optimization and control for a long time. And in terms of some of his achievements, he got his PhD from CMU and then joined after a postdoc at UPenn. He joined Tufts University, and after joining Tufts, he's been awarded. He has received a number of awards, including the NSF Career Award. Also, 3 Best Student Paper Awards. He has also been involved in a number of professional activities, including recently proceedings of the IEEE special issue that he was the lead guest editor on, which was data-driven learning and control. He was also a guest associate editor for IEEE Control Systems Letter special issue on learning and control. And he's currently serving as a technical area chair for IEEE 2020 SLOMAR conference, which is happening right now. And in addition, he's been involved in a number of other technical activities. So it's a pleasure to have Usman back at Rutgers, this time virtually. I think he came to Rutgers a while ago, I don't remember, but at that time, his research was way different than this. So it's a pleasure to have him here and look forward to hearing your talk. All yours, Usman.
All right. Thank you very much. Thank you, Wahid, for a kind introduction. Thank you, everyone, for attending. I know today is an exciting day, and trust me that when we scheduled this, I did not realize it would be the day after the election day. But it is what it is, and hopefully, this seminar will be as exciting as the elections. As Wahid said, I visited Rutgers back in 2017, August 2017, I guess. And that's when we recently started some of this work. And our focus at that time was heavily on distributed optimization over directed graphs. And I will introduce that work as well and kind of use that platform to launch into this non-convex stochastic problems. So more or less the subtitle of my talk, distributed stochastic non-convex optimization, is the real title, but the distributed machine learning is more like a marketing type title. So before I start, of course, I have been blessed to work with some excellent students, and the work here, of course, sits on their shoulders. And I also acknowledge the support of NSF that led us to hire students and do this research. So I'll start with a global overview, and especially given with this the nature of the people who are attending, this should be a no-brainer, but we know that data is everywhere. And we have seen exciting problems in learning from data in many different areas of, let's say, image classification, financial transactions, even political campaigns, advertisement, etc. And if we realize the size and scale of the problem, so imagine that the number of photos I have on my phone, let's say, I have about 48,000 pictures. And if we want to learn about some properties, some aspects of identifying people, identifying bikes or red lights, traffic signs, collecting all of these images, which exist across all of our devices to a central location, is just a huge communication and computational nightmare in a way, right? And right now, this is done with the help of very, very, very large data centers, which consume a lot of energy, very expensive to maintain, etc. So what we have been looking into for a while is to design distributed algorithms, and it started from sensor networks, but then sensors started moving, so you moved into mobile networks, multi-agent networks, then social networks came in, where we started looking into opinion dynamics, voting models across when the agents are individuals. And more these days, we started looking into this distributed optimization machine learning type of problems where the data is distributed, the data is very large, and there are many individuals who possess this data. A key concern is, of course, privacy. Another concern is the proprietary nature of the data. I mean, it could have some financial value to me, and I don't want the data to leave me, or it could be just that it has some My medical records are private, pictures of my family are private, etc. And that's why distributed algorithms help us to address these aspects of the of learning, where we can keep the data private, the data never leaves the device, etc. So this is again a classical example, very standard for especially the people in this group. So imagine that I've been given a collection of labeled images. One class is the stop signs, which are marked as a star in some high dimensional space. So just think 2D here. And another class is the yield signs, which appear as a triangle in this space. And my goal is that given this data, I want to learn a classifier, which I depict as a line or a hyperplane, such that I can maximize my classification accuracy or minimize the loss in classification. So for instance, you look at the red hyperplane here, we can see that if I declare that anything above red is a star, anything below red is a triangle, the red classifier has 6 points that are not classified correctly, and the green classifier has all the red points and in addition a green point, so it's 7 points. So we can see that if I change the hyperplane, this prediction loss will be different. And the problem that we want to solve is that we want to pick a hyperplane, X star, a classifier, that minimizes some prediction loss. So this prediction loss could be a squared error, which is just yj minus yj hat squared, could be some other function which is not that nice. The prediction itself, y hat, could be a different function. And you can see that different predictors and different losses can lead to a different function class. So for instance, in signal estimation problems, we are interested in finding signals from a measurement, which is signal plus noise. And typically, if the the model is linear and the noise is Gaussian, we know that the optimal estimator is also linear. So when we minimize the squared error between an estimate and the truth, we are in the signal estimation regime where the functions that you want to minimize are quadratic. The image classification example that I gave you before, if we choose logistic regression for prediction and losses, then the resulting function becomes convex. I can add a regularizer to it so that it becomes strongly convex. And we all know that recently many problems, deep learning, neural networks, reinforcement learning, phase retrieval, etc., have these functions that we want to minimize in order to learn a certain parameter, and these functions are non-convex. The approach that I'm going to take today, and which also comes from my research largely, is first order methods. And when I say first order, I mean that I'm allowed to take first derivative of this function f. So of course, when I say the function is differentiable, I'm taking the derivative, it adds certain properties to that function class. And since I'm using first order methods, what I am interested in finding is a point where the gradient is 0. So let's call it x star. And depending upon whether I'm in the quadratic, convex, strongly convex, non-convex regimes, this point x star will have certain different properties, and I'll explain them in a bit. So my goal is to minimize functions when the functions could satisfy different properties, and these functions I'm allowed to take gradients, so these functions should be differentiable in a way. So in general, the most general function class that we consider is this class of functions which are L-smooth. So L-smooth functions by definition are differentiable, they are continuous. And in addition, what we assume is that, or what we enforce is that this function is bounded above by a quadratic at every point. And this quadratic is controlled by L, this capital L. And of course, it has a uniform lower bound, which we say f star. So in general, when I will say in this talk that a function is smooth, I'm only talking about this one property. It's not necessarily convex or strongly convex or anything else. So in general, when you want to talk about non-convex functions, the only assumption we use is the smoothness. The next class of functions is this. It's a special case of invex functions, if you have heard of them. But it's a function that satisfies the Polyak-Loyashevich condition in addition to being smooth. And this condition implies that every stationary point is a global minimum. So I tried to give an example here where this function is not necessarily convex, right? Because if I draw a line between these 2 points, the function lives above the line. But the stationary point is a global minimum. We can have multiple of them. In addition, it satisfies this property. So you can see that this property somehow forces some restriction on how the functions can grow, how the gradient can grow when we move away from the optimal f star. The next class is something which is more familiar to us, convexity. So a function is convex if it lives above all of its tangents. So this is what I'm trying to show here. In addition to the standard definition where you take 2 points on the function, draw a line, the function lives below. And something which is also of huge interest to us is strongly convex functions. So in this class of functions, we assume that the convex function, smooth convex function, because smoothness is universal here, at least for this talk, is bounded below by a quadratic. And this below quadratic is controlled by something we call mu. So you can see that a convex function that is bounded above by a quadratic and bounded below by a quadratic is smooth and strongly convex. And that is something which will come again and again in this talk. For functions that satisfy the PL condition, not necessarily convex, and strong convexity, we have this this notion of kappa, where kappa is the ratio between L and mu. So remember, for smooth and strongly convex function, L is the quadratic upper bound, controls that, mu controls the quadratic lower bound. So for a quadratic function, L over mu will be 1. But if you think about an ellipse, then one direction is much bigger than the other direction. So the upper bound will be the larger one and the lower bound will be the lower one. So the condition number will be, let's say, 10 for an ellipse, which is like 10x squared plus y squared. And I think these properties are easier to kind of remember in this context, in this Venn diagram type of a representation, where the class of L smooth functions, if I restrict, then there are several other classes which live inside. Convex is one. Functions that satisfy Polyaklo-Yashevich condition is another one. And then where convex and the PL condition overlap is something we call strongly convex functions. And since we are interested in finding a stationary point x star where the gradient is 0, we can see that when a function is non-convex, a point that satisfies this property or a stationary point could be a minimum, maximum, or saddle point. When the functions are PL or convex, we know that the function has a unique minimum, but many points can achieve this minimum. So the function value at x star is the unique global minimum, but x star may not be the unique minimizer. But when I talk about strongly convex function, I know that f of x star is unique and x star, where this is achieved, is also unique. So I think this is something which we'll just use for the purpose of intuition, and I'm happy to discuss more after my talk on these classes. And because I said we'll do first order gradient based methods, so of course that I'm going to use the simple intuition of gradient descent, where the idea is that you compute the function value at this point xk and evaluate the gradient. And in order to decrease this function value, we take a step in the direction of the negative gradient. And how far we can go will depend on the size of the step. So the resulting algorithm is this well-known gradient descent, where the step size on how much I want to move towards the minimum is given by alpha. And then this is a negative gradient. So the best estimate I have of this x star can be refined a bit with the help of this algorithm. And of course, the different function classes will lead to different guarantees on how much I can reduce the function value at my new iterate versus my old iterate. So this is something which we kind of have to remember at the back of our minds. So gradient descent, and just for the purpose of intuition, is just the fastest first order algorithm. And I think it's going to be very natural to at least this group, where we know that it's not the fastest. And it's not the fastest because it treats the functions that are quadratic and ellipse in a same fashion. So for instance, a quick intuition can be seen here. So here I have an ellipse, and this is the level curves of a ellipse in 2D. So think of this as 10x1 square plus 10x2 plus x2 square. So the function is bounded above by something like 10 or 11x square, and bounded below by something like x2 square, x1 plus x2 square. So the condition number is going to be, let's say, 11 over 111 or 10 over 110, right? And this can be applied to general function classes. So take a point on this level curve. We know that gradient descent takes a step in the direction in the direction away from the maximum growth. So the maximum growth at this point, the first blue point, is here. So gradient descent will push me here. But you can see that this direction is not towards the general direction of star. You can see that if the function becomes narrower and narrower, kind of stretches, this ellipse stretches in one direction, then this direction is going to be more and more parallel to the horizontal axis, and the convergence will get more and more slow. And this is what we see typically. So for L, if L over mu is 100, then the first 25 iterations of gradient descent will put me somewhere here. So to get epsilon close to the minimizer x star, gradient descent iterations are exponential, converges exponentially fast, but with a factor of kappa. So here, the gradient descent for some accuracy epsilon will require 100 times log of 1 over epsilon iterations. So naturally, we can accelerate this by using some ideas from second order physics, where what the intuition is this. So the gradient is taking me in this direction, the red direction, but see that x1 minus x0, which is like the momentum, is going in this green direction. So it turns out that if I take a linear combination of the momentum and the gradient, I will be somewhere here, which is the new blue, the third blue iterate, which is closer than what the gradient alone was taking me. And this is what we can observe in experiments also, that with the addition of heavy ball momentum, gradient descent plus heavy ball in 25 iterations gets much closer to the star versus the red, which is gradient descent alone. And the dependence in this case is square root of kappa. So if kappa is 100, you can see that heavy ball or accelerated version will reach a certain accuracy, square root of kappa, or 10 times faster than where the gradient descent would be. This idea, the issue with this type of momentum is that we can only prove that this works for quadratic functions, for functions that look like ellipses. And we can go into the detail of that, but Nesterov, who was a student of Polyak, who came up with the heavy ball acceleration, has this Nesterov accelerated method where we can prove these properties for a much larger class of functions. And it's also noteworthy that this type of Nesterov or Polyak acceleration may not give us the same performance improvement when the functions f become stochastic or non-convex. So with this setup, we go back to my function dependency diagram, this Venn diagram, wherein now I'll try to characterize performance metrics and rates. So think about gradient descent again. So remember, for the non-smooth problems, there are multiple points x star or stationary points to satisfy the gradient equals 0 property. So what we typically do, or what we typically quantify, is the norm of the gradient at the iterates of the algorithm gradient descent. And we want to show that the norm vanishes as the algorithm proceeds, and the rate at which it vanishes is 1 over square root of k. When the functions are convex, remember that convex function has a unique minimum, could be achieved at many different points. So typically, what we show or what we characterize is the difference between the function value at the iterate of gradient descent and the minimum value. And we know for convex function, gradient descent has a rate of 1 over k. And when we talk about Polyak, Loyashevich, or strongly convex functions, remember, for strong convexity, x star is unique. So we can actually talk about this quantity, which is xk minus x star, because x star is a unique point where this can happen. And for Polyak, Loyashevich, and strongly convex functions, we can show the gradient descent converges exponentially fast to the stationary point x star. And this exponentially fast is something which I'll keep repeating, but if when it applies, and I'll call it linear, because if an exponential converges, when I view it on a log scale, it looks like a straight line, a linear line. So what happens when the data becomes distributed? So for example, suppose that we want to solve a simple linear regression problem. I have these 18 points, and I want to fit a line to these points, but these points are distributed to different agents. So you can see that the purple agent, the magenta agent, has 4 points, and green agent has 5 points. But if the green agents were to operate only on its own points, then the estimate of the line, which is the straight green line, has nothing to do literally with the black line. So the trend was down at a certain slope, and the green data is telling me the trend is up, etc. So you can see that when the data is distributed and I do some learning, which is just local gradient descent, where this function f of I represent the loss function of fitting a line through these 5 points, then gradient descent will converge to the minimum of this f of I, which is my local loss, but that has nothing to do with the global problem. So local gradient descent does not lead to agreement. So every node converges to its own estimate. And of course, if there is no agreement, then the nodes cannot agree on the optimal solutions. And when we design distributed algorithms, we require that each node agrees on the same solution, and the agreed upon solution is the optimal. So here I have now, I'm ready to describe the first kind of a problem formation for distributed optimization. And what we have is this. So think about a network of nodes. They are interconnected, by which I mean that they can exchange information. And every node in the network possesses some data. And when it converts that data into the classifier or predictor and the loss functions, it gets some function f1. So every node has f1, f2, f3, f4. These functions, the common parameter is x, which we want to learn together. And the coefficients, for instance, of these functions will be parameterized by the data. And this is not necessarily a directed, an undirected graph. For instance, some edges could be one directional, but typically we assume it's strongly connected, which means between any 2 points, there is an edge. So each function is private. So the node one is not allowed to see the functions of any of its neighbors or any other node in the network. For now, I'm going to assume that each function is L smooth, bounded above by a quadratic, mu strongly convex, bounded below by a quadratic, and convex. And the nodes communicate over a connected graph. And in this setup, if you recall, this global function f has a unique global minimizer x star such that the gradient of at this point is 0. Okay. So this is the first kind of a very well-known algorithm, which Mert here is related to the same people. So I think it was a paper by Nadic and Osterglar, if I remember correctly. But what this algorithm does is it's called distributed gradient descent. So remember that the black equation, when I look at, when I put this R as node I, then it's the local gradient descent. But instead of doing local gradient descent, this equation mixes the information within a certain number of nodes and then takes a step in the direction of the gradient. So for instance, node 1 will look at or will ask nodes 2 and 4 for their estimates of x star, and then uses some weights, W11, 12, 14, to form a linear combination and then take a step in the direction of the negative gradient, right? The weights have to satisfy certain properties. So if the weights sum to 1 across rows and across columns, which means that across incoming edges and across outgoing edges, then this is what we call a doubly stochastic matrix. And under this property and under that the function is smooth and strongly convex, we can show that distributed gradient descent converges linearly, so on a log scale, which means exponentially, up to a steady state error. So it'll go down very fast, but then there will be a flat error. So actually, a footnote here is that this algorithm was proposed for alpha k, where the step sizes were time dependent, and they showed that if alpha k is chosen to be 1 over k, or something with that proportion, then the convergence is to the true x star, which is the minimizer of the sum function. However, the rate will be dictated by the slow step size is 1 over k. So if you want to keep the rate linear, which is exponential convergence, then there is an error that we have to incur. There are other strategies that we can discuss, but this is the basic idea. So this is the summary so far. Gradient descent converges linearly for smooth and strongly convex problems. And the dependence is kappa, where kappa kind of quantifies how much of the function is an ellipse versus a perfect circle. Accelerated gradient descent heavy ball is much faster than gradient descent, because if the function looks more like an ellipse, then the dependence is not kappa, but square root of kappa. And distributed gradient descent converges linearly and then incurs a steady state error. So this is the first kind of takeaway from this point, that, or from this talk, which I'll discuss algorithms where we want DGT first of all to converge linearly to the minimizer, right? So we want it to keep going down, just like gradient descent. And then on top of it, we'll see if we can build some acceleration to it. So it kind of pushes it faster than the non-accelerated version. But before I address these questions, I have to understand why is there a steady state error in distributed gradient descent when I choose a constant step size. And remember, constant step size is needed for linear convergence. So this is the first algorithm that comes from our group. And the motivation came a few months before we published our papers. And that was for undirected graphs. And this is the basic idea. So remember that in the distributed optimization setting, I want to minimize a function, which is the sum over some nodes in the network, all the nodes in the network. In other words, I want to search for x star such that the gradient of this cost is 0. And remember that this is the sum gradient. What DGD does, because this is just a local gradient, you can see that if I insert x star everywhere where I have xk, then the result is not X star. In other words, X star, which is the truth, is not a fixed point of this algorithm. And the reason is this. So suppose that all of my neighbors knew X star, they sent it to me. So X star is now not a function of I or R. Everybody has the same. So these weights sum to 1. So I have 1 here, minus alpha times the gradient evaluated of at X star of my local functions function Fi. But remember that this quantity is not necessarily 0. What 0 is the sum, right? So what we get out is not necessarily X star. And this is what we call a local versus global dissimilarity bias. Because if I were to have capital F or the sum gradient here, then this quantity will be 0. So you can imagine that how far each Fi is from the sum Fi will quantify the performance loss in a way. And if all of them are to be turned out to be exactly the same, then the same X star would minimize, which is not true in general for distributed optimization problems. So the intuition came from this dynamic average consensus algorithm, which was done in about 2008, I think, where we replaced the local gradient, the gray part here in the gray equation, with an estimate of the global gradient. Okay, so instead of implementing local descent direction here, I'll take a descent in the direction of yk, and I'll hope that this yk, with the help of some other iterations, converge to the global gradient. And this is exactly what the algorithm looks like. So the second equation, so remember, not local gradient, but yk. It should be yki because it's not r. And then this yki is updated with this second equation, where you can see that the local gradients appear in the second equation. And you can show that the second equation tracks the sum gradient. So combination of the true, as k goes to infinity, this yk becomes the sum gradient without even looking at the neighborhood functions. And this algorithm converges to X star, which is the truth. X star is the minimum of the smooth and strongly convex problem, and it converges linearly. And the term gradient tracking is what we represent equation y with, where y basically tracks the global gradient in the network. Our contribution was that we showed this algorithm works for row stochastic weights in the first update and column stochastic weights in the second update. And it's fundamentally, people always use doubly stochastic weights, but when you use row stochastic and column stochastic, it turns out that this application is applicable to arbitrary graphs, not necessarily undirected. And the undirected version becomes a special case of this algorithm. And we have, a lot of work has been done on this particular form of distributed gradient descent with gradient tracking and with these type of weights. And what we have done is also that we have remember the heavy ball acceleration to this AB algorithm, where each function has a momentum term depending upon only of its local kind of iterates. And we can have certain nice, show certain nice results. So this is a summary slide.
Can I interrupt you?
Yeah.
Can you go back to the previous slide?
Yeah.
So I guess from a functional perspective, now you are asking each node to share both their iterate and their gradient, as opposed to the original.
Their estimate of the gradients.
Right. So now they are now sharing more information with each other, basically.
Yeah. So X is p-dimensional. So they'll, in the basic algorithm, you share p dimensional vector. Gradient here, y is the estimated gradient. It's also p-dimensional. So now you share 2p with your neighbors.
Okay.
Yeah, so communication becomes double.
Okay. Yeah. Just wanted to clarify that. Thank you.
So this is a summary slide with respect to the work, several extensions of the methods that I've described. We have developed some of them. Then there is our work on time-varying random graphs, and another work on gossip-based protocols, which basically take into account dynamic moving agents, mobile agents, let's say, dynamic communication graphs. Then there is work on some non-convex analysis by Gesualdo Scuteri without explicit rates. There is work on asynchronous delays, etc. Condition number wise, what we have shown is that the AB algorithm has a condition number of kappa square. So remember gradient descent, and AB just tries to mimic gradient descent, but the condition number dependence is actually kappa square. We kind of can see that it should be kappa, but our proof technique doesn't lead us to something better than kappa square, at least now. For undirected graphs, people have shown kappa. For undirected graphs, our own methods have shown kappa to the 5/4, but this is not only for smooth and strongly convex functions. This is a slightly bigger class of functions. When it comes to acceleration, we cannot. So remember, I showed you that we added momentum to AB. we cannot actually prove that adding momentum converges faster than the version when I don't add momentum. So this is still open in a way. We can observe this. For undirected graphs using Nesterov momentum, the kappa dependence is shown to be 5/7. We have shown for directed graphs that numerically we get acceleration, but for directed graphs, convergence of with Nesterov momentum and acceleration both are open, and we can discuss further if needed. So this is the summary slide on the algorithms that I've discussed so far. So remember that gradient descent is this black curve, converges linearly. Heavy ball momentum converges faster than gradient descent for problems when condition number is 100. Distributed gradient descent without gradient tracking has a steady state error, but AB with the help of gradient tracking over directed graphs removes this dependence on the steady state error, or removes the steady state error completely, and we get linear convergence. And when I add momentum, you can see that it actually becomes faster even than gradient descent, but we are unable to prove this acceleration. Now the question is that, and as I promised in the title of my talk, stochastic non-convex, what happens when the gradients are imperfect, which means that I'm not allowed to take the true gradient, but a noisy gradient. And we can see, at least from a intuitive perspective, from intuition, that full gradient, if every time instead of the gradient, I have gradient plus noise and the variance of the noise is nu square, then full gradient problems are these, which are nice looking. And gradient tracking, this blue dot is the AB algorithm that I showed. But when I add noise, then we lose everything. So we can still see that there is some linear convergence aspect, but there is steady state error to even algorithms that would converge without just steady state error. And it's intuitive that the steady state error is going to be a function of the variance. Actually last year, this paper came out, which explicitly provided a bound for smooth and strongly convex functions. And remember, this is stochastic, so we have an expected value here. And we can see that the steady state error converges linearly. The error, which we call residual, converges linearly for distributed stochastic gradient descent up to an error ball, where the size of the error ball is this expression. So you can see there is eta. Let me describe eta in a bit. Nu square is the gradient variance. So if nu square goes away, we still have eta, which means that if distributed gradient descent, if there is no variance, then there'll still be a steady state error. So this quantity is what is here in the purple curve. And this eta quantifies the difference between the local function, my function fi, and the sum function, global functions, where we want to kind of converge. So what happens that gradient tracking eliminates this eta, right? So if I do gradient tracking, this term will go away, but then the nu square, the stochastic thing remains. And of course, if I do gradient tracking for full gradient problems, then eta and nu square are both zeros. So now I'll talk about distributed stochastic optimization for non-convex problems, and I'll look at the same algorithm that I showed you, but in a different setup. And this is the setup. So same as functions are distributed over a network, each node has F1, every node has F1, F2, F3, nobody's allowed to share. Measurement is done like this. So at every time k in the online or streaming model, every node takes a noisy measurement of the gradient, which means at the time iteration k of the algorithm, I take gradient of f plus noise, let's say, or we have like slightly more general properties. And the other model will be, measurement model will be with this offline or batch model, where we don't take noisy samples of the gradient, but I am in possession of, let's say, 50,000 images over which I want to do learning. So the data I already have in a batch, in a box, and my goal is to do learning over this data, where I'm not collecting it in real time. Nodes communicate over a strongly connected graph. So remember that gradient tracking eliminates eta, and I'll show you the exact expression as well, actually, which is the local versus global dissimilarity bias, but the variance remains. And now for the rest of my talk, I'll consider problems where we can quantify the performance of gradient tracking, distributed stochastic gradient descent for different function classes, and we look into ways of eliminating the dependence on the variance as well. So the first up is smooth non-convex functions. So we're basically here in the broadest class, and all we can assume is that it's smooth, L smooth, so bounded above by a quadratic, and have a lower bound. And I'm now looking at the online setup, where instead of the gradient of fi, I take an unbiased estimate of the gradient, which has a bounded variance nu square. So instead of the gradient here, I'll just throw g, right? G is the Think of G as gradient, true gradient plus noise. And what is the behavior for general non-convex, the largest function class? So this is the first result. I think immediately from the theorem, you have to, so don't look at the entire statement, but first note that the quantity that we are quantifying is what we call mean squared stationary gap, which is basically, as I described before, for non-convex function, we want to find a sequence of iterates where the gradient vanishes in expected sense, because now we have stochastic gradients, and this has an upper bound. So it and the rate at every k, for every capital K greater than 0, is given by these 4 expressions. So the first thing to note here is that the bias eta, which was because the local versus global dissimilarity is eliminated. But of course, that the error terms due to nu square remains. So there will be some steady state error. And here, remember that constant step size, so alpha is fixed. Later down the road, I'll show you some work on decaying step sizes. This result is non-asymptotic, which means there is no limit here. It applies for every k. Linear speed up. So this is something interesting. This algorithm performs n times better than the centralized SGD. But here I'm also, it's a little bit of a loaded statement. So centralized stochastic gradient descent at every iteration of the algorithm computes 1 gradient. And in distributed setting, at every iteration of the algorithm, every node is computing 1 gradient. So you can see that the information the distributed has is n times more than the centralized. And we can show that this n times more information results in an n time better performance. And in that context, I'm saying that if your machine has a maximum capacity, you replicate this same machine over a network, then the performance is going to be n times better than the centralized machine. That is what we quantify as linear speedup. And here again, I am not accounting for the communication between the machines. So of course, this improvement comes because of the communication and parallelization of data in a way. And network independence, we can show that after a finite time, so when this k is greater than some k1, which is finite, and we have an exact expression for that, which I didn't put here for the purpose of simplicity, we can show that the performance, or the bound here on the right side, does not have any network related terms. So it does not have 1 minus lambda, where lambda is the second largest singular value of the weight matrix W, for instance, for those who know. So that's the other. Another kind of a small thing here is that for fully connected graphs, we know that the second largest singular value of the weight matrix is 0. So you can see that these 2 terms for lambda equals to 0 will disappear. And for fully connected graphs, GT-DGD actually gives me the performance of centralized mini batch SGD, where by mini batch, I mean that this centralized stochastic gradient descent samples n gradients per iteration of the algorithm. So that's the mini batch term. Next to the next function class, which is still non-convex, but satisfies in addition this condition, we can show that the different metric, remember that the metric is different because the function has different properties. So we can show that the function value at an iterate of the node minus the truth. Remember, f star is unique for functions that satisfy PL conditions. In the limit, in the asymptotic sense, have this bound, so converges linearly to an error ball. Error ball is a function of the variance and the function of the network, where lambda kind of characterizes network. And again, the network disappears when lambda is 0. And we can show linear, first of all, no bias due to eta. So there's no local versus global dissimilarity thing here. We can show linear speedup, which means that this performance matches the mini batch SGD, which computes n gradients at a time, or n times faster than SGD, which computes 1 gradient at a time. And remember that functions that satisfy PL condition actually have strongly convex problems as a special case. So this result applies for strongly convex problems as well. We can show when the gradient is 0, when we use full gradients, which means there's nothing stochastic, nu is 0, then this bound becomes 0, right? This is 0, this is 0. And the function, this error decays linearly at this rate, where the kappa dependency is kappa 5/4. And this is what I mentioned before. So the best known under strong convexity, the best known dependency is kappa for a distributed algorithm with gradient tracking. But kappa 5/4 is applicable to a slightly larger class of functions. And this result also is an improvement to the best rate known for distributed algorithms under the PL conditions with full gradient. And of course, for those of you who know this type of stochastic gradient type of algorithms, we know that if we choose a decaying step size, then the dependence on the variance can also be eliminated. And this is what we can show in both. This is the almost sure result, but we can also show in the mean squared convergence. Basically shows that if we choose step sizes which are decaying 1/k, and there is a larger class which comes from stochastic approximation type of arguments, then the probability that nodes will reach agreement is with probability 1, and at every node the function value will reach the minimum is also probability 1. The rate is something like 1/k or upper bounded by that. So now I'll quickly go over batch problems, and by batch problems I mean that every node in the network has a collection of images. So I have a collection of 100 images, but he has a collection of 40 images, somebody else has a collection of 5,000 images, doesn't matter. Our collection of images could be arbitrarily different. So if we want to do animal classification, I may have only seen an elephant, somebody else may have only seen a lion, and somebody may have seen small number of images, but across a larger number of classes. And if I do, you can see that depending on the size of my data, the cost function, my local cost function fi now is summed over the component, my images. And depending on the size of my data, computing gradients could become very large. So if I have 40,000 images on my phone, then computing gradient at every image and summing them together is going to take me a long time. So the stochastic version of this would be sample one image from your local data and then use that tau. Tau is basically a random index that samples this image, and implement gradient descent that is just focused on this tau. But you can see that this algorithm does not use gradient tracking. And so first of all, there will be errors due to the local versus global bias. And there will be error due to the sampling. And you can imagine that one error I can eliminate with the help of gradient tracking, and another error I'll show you we can eliminate with another trick. So this is what we call the gradient tracking and variance reduced framework. So for those of you who have seen centralized optimization type of recent work, you'll be very familiar with this approach. But the basic idea is that take one node who knows all of this local images. The node samples one image from its data set, implements a variance reduction procedure, which basically estimates the entire data set. And this is kind of used loosely because it estimates the sum gradient at the local node. So variance reduction helps me to take one image from my bin and then estimate the sum gradient from this one sample. And then over the network, when we do gradient tracking, we'll use this estimate for gradient tracking. So we have sample, estimate, and then gradient tracking. So there are, in centralized algorithms, there are popular methods, Saga, SAG, Spider, Sarah, etc. They're applicable to different function classes with different rates. What we have done is for Saga, SVRG, and Sarah, we have shown, we have developed distributed variations which implement gradient tracking and variance reduction in the same framework. So this is, I give you a quick overview of how the Saga approach works. So Saga is a method for variance reduction. The idea is that, so remember that node I has, let's say, 5 images, 1, 2, 3, 4, 5. So node I at some starting point x, 0i, node I computes these 5 gradients, then sums them up and uses that sum to do gradient tracking, and then uses that gradient tracking to update x. So something is kind of embedded in this block. But at the next time sample, it picks up one element randomly and only updates that gradient, and then repeats the same process, sums them up, do a round of gradient tracking, update x. And then at the next iteration, does the same, like sample another point. So this requires storage. So you need to know all of these gradients in order to compute the sum and then do this replacement. And this is where I showed network. So after you compute the variance reduced estimate, you mix it over the network with the help of gradient tracking, and then mix the nearby iterates x in a neighborhood to implement the algorithm. And then the same process keeps repeating. What we have shown is that for strongly convex problems, we have shown that over batch problems, GT Saga, which only computes one gradient at every iteration, converges linearly through this minimizer of the global minimizer of the smooth and strongly convex function. For non-convex functions with Polyak-Loyashevich condition, it's shown linear convergence again, network independent rate. And for non-convex problems, we have shown linear speedup, network independence rate, and some provably fast convergence compared to the existing work in certain regimes, which I just described as large networks here, but I can explain a bit more if needed. So the next architecture for variance reduction is this famous algorithm called SARA, which stands for Stochastic Recursive Gradient Algorithm. So this algorithm does not require storage, but it requires some additional properties of the network, and I'll explain this in a bit. And here I'm assuming that, yeah, so imagine node I. So what node I does is that it computes this gradient over this entire local data, right? At some time, let's call it capital T, and then keeps updating this iterate X with the help of samples from the gradient. So it goes until some capital T iterations and then computes the full gradient again. So you can see that in the previous setup, I was sampling and then computing the full gradient at every iteration. And that's why I needed storage. In this setup, I don't need storage, but periodically I'll compute the full gradient. But in the meantime, I'll just do sampling. And if you look at two different nodes, then they will, of course, do gradient tracking over the estimates of the of their local gradients, and also do mixing on the x's, right? So this is node R, node I. And one thing you can immediately note here that for decentralized implementation, that computing this gradient depends upon the size of my local data. So for instance, if I have 5 images, let's say I compute this gradient in 5 units of time, versus somebody who has 50,000 images, they would need 50,000 units of time to compute this gradient. But the algorithm, this mixing cannot happen unless this gradient is computed. So in order to start mixing, I need to wait for the node with the largest data set to finish this gradient computation, and then the algorithm would kind of proceed. And this is what I mean by it doesn't require storage, but requires additional network synchrony, because when the data sizes are different, this gradient computation will require different, let's say, wall clock time. So gradient tracking plus this particular method of variance reduction, we have shown some strong results for this algorithm. So first of all, we have shown that an algorithm that uses SARA-based variance reduction, then use the estimate of this variance reduction to do gradient tracking over the network, and then also iterates with their neighbors. So as Wahid mentioned, 2 communications. Then this algorithm, at each node I, the iterates follow this property. So we were able to show convergence in mean squared and convergence to probability 1. And actually the first is implied by the second. We were able to show something even stronger. So this is like a few of my last slides now. So suppose that I want to solve this problem over batch data. So every node I has m data samples. So here I'm assuming m is equal across all nodes. So everybody has the same data size. There are n nodes in the network. So the total number of points are nm. So imagine that from a centralized perspective, I want to minimize a function that is a sum of n times m functions, right? And not necessarily, this is smooth and non-convex, so not necessarily convex. So a question we could ask, how many gradient computations are required to achieve an epsilon accurate solution? So there's something which is typically called epsilon accuracy of the algorithm. So it turns out that GT-SARA, the result is here, but I will show you this last statement where it shows that in a particular regime where the number of nodes follow certain property where this capital N is little n times little m, then the gradient computations we need is given by this. It's 1 over square root of n and 1 over epsilon. It turns out that this gradient computation complexity matches the best optimal, not even the best, the optimal algorithmic lower bound that was derived a few years ago in the SPIDER and the SARA papers. So it turns out that GT-SARA matches the algorithmic lower bound, which is for this class of problems, and I want to minimize a sum of n times m smooth non-convex functions. And you can actually, if you zoom in into this bound, remember that this capital N is little n times little m. And if m is very large, then this bound can be satisfied, right? So, so we call it a big data regime, and we say that GT-SARA is optimal for this class of problems in the big data regime. And we can further show that this performance here is that I showed before is independent of the variance, independent of the local of the global similarity bias. So variance is scaled by variance reduction. Local versus global bias is scaled by gradient tracking. We can show network independent. That means that after a finite number of iterations, network doesn't matter. Linear speed up, again, that GT-SARA is n times faster than the centralized SARA. But again, the notion is one gradient centralized SARA is n gradients of GT-SARA. So having this n times better performance is more of a, it should be kind of a byproduct of decentralization. It's not true for every algorithm, right? So here is my second last slide. This is just for smooth and strongly convex problems. I just wanted to give you an intuition of how these things kind of look like. So imagine I want to fit a line on these 100 points. Every node in a network has 1 point. So imagine I have 0, 0, somebody has 1, 2, 2, 3, -4, -5, etc. So everybody has these points. So remember that if I only looking at my data point 0, 0, if I want to fit a line, slope and intercept, any line that passes from this point works, right? So this is, I need to collaborate with my neighbors or over this network in order to learn the true line, which is this blue dashed line. And this is how the algorithms look like. So the second figure here, so you can see everybody starts with a random estimate of the slope and intercept. And I'm only showing 10 agents here. And you can see in this top last figure, top row, this is the AB algorithm that I showed you. And you can see that the nodes come together. So they agree first, and then they agree on the minimizer. So you can see that there is an effect of network independence going here because they agree first. And then after that, network doesn't matter. They all kind of together move to the truth. And this is distributed gradient descent with constant step size. So I showed a steady state error, which means that the node do not even agree, actually. Or actually, if it's a slight variation, they can agree on a suboptimal solution. And here I have distributed gradient descent with decaying step sizes, which so the black curve actually is going to X star, or like the error is going to 0, but at a very slow rate, which is like 1/k. I don't exactly remember. But the centralized gradient descent is linear, exponential, and gradient tracking is also linear. So last slide, I mean, I talked about, in the context of distributed optimization, I talked about gradient tracking, that how it allows us to remove the local versus global bias when local function is not close to the, let's say, the sum function. We showed linear convergence for smooth and strongly convex problems. We showed acceleration, but we haven't proved them, right? The analysis is hard. Then for online stochastic problems, I showed you how decaying step size can eliminate variances. We can have some very strong theoretical statements, rigorous statements where we talk about convergence and probability, etc. And then I talked about offline stochastic problems where we have a batch data and we only sample from that batch. And we showed that adding variance reduction to gradient tracking actually recovers optimal performance for non-convex ISM problems with the particular choice of methods. I talked about linear speedup and network independent convergence behavior, which are two kind of recent but well-known notions, the properties that one would expect from a distributed algorithm. So when often we design algorithms, we try to prove these properties. And I showed regimes where there's certain regimes where in a way decentralized methods outperform their centralized counterparts because they are n times faster. And my last slide is a bit of a shameless advertisement where, as Wahid mentioned, I am worked with Wahid and some of my very well-respected, well-known colleagues on this proceedings of the IEEE special issue, where we have a set of 12 papers on very modern recent work on optimization for what we call data-driven learning and control. It's a very good overview on things that recently have been done and the things that are still to do if you are interested in these type of learning and control problems. And it has this special issue has papers on distributed, on centralized, on variance reduction, accelerated methods, stochastic non-convex problems, second order method, zeroth order method, etc. So this could be a very good starting point if you want to learn more on the progress along these lines. So with this slide, I'll conclude my talk and I'll thank everyone for patiently hearing.
Thank you, Usman, for the wonderful talk. We'll just appreciate the virtual round of applause. So at this point, I'll open the floor for questions. Anyone want to jump in?
I have a quick question, if possible. Thanks for the nice talk, Usman. I was wondering about the non-convex regime where you showed us some results, right? Like the expectation gradient has some bounds. But
Yeah.
you know, in non-convex setting, the technique of random stopping is also used. If you have k iterations, imagine that you stop randomly in between.
Yeah.
That convexifies the problem and gets you sometimes better sort of control. For instance, Gadi-Milan type of papers on your error. Because you are stopping randomly, it can help with your error. But when things are distributed, it's not clear because everybody has a random index, and you know, that may not be clear. But has anyone thought about this, like using this random stopping type of approach?
So you may be familiar with the variance reduction methods like SVRG and SARA, where so this is actually a double loop method. So an inner loop runs on this iterate capital T, and then outer loop runs on this. And I try to, show it in a way so that it's easier to kind of explain. But what happens is that when the inner loop finishes, this last iterate is either the last iterate or randomly chosen across all of the inner loop iterates, or an average of all of the local inner loop iterates. So you can show that this algorithm converges. I'm not exactly sure that there are. So when these papers are going to talk about one particular choice, which leads me to believe that there is no one true answer, but I may be wrong. But I mean, I know about random stopping type things, but I haven't looked at them from the decentralized perspective.
Sure. I think like basically they can also apply to non-finite sum problems.
Yes. True.
Basically, it's the streaming setting. But maybe it's never thought of in the distributed sort of setting.
Yeah.
But
I mean, we could look into this, that if you want to stop randomly, then every node can just stop randomly, but then maybe the other nodes who decide not to stop can still iterate, but this node just fixes on its iterate. And then maybe the properties we can guarantee is on the average. Yeah, it's a good point. We can think about it. Yeah.
Thanks very much. Thanks.
Yeah, thank you.
So we have probably time for a quick last question. Anyone has any thoughts? Because we are up at the top of the hour. So Usman, I had a very quick question about the network effect that you mentioned, which is that the network, like even in the simulation you were showing that the network becomes irrelevant once they agree, but while they are trying to agree, the network still plays a role. So you are saying that within the big scheme of things, that phase of the algorithm doesn't matter that much, or it's not the major bottleneck, or did I misunderstand?
No, so the network independence results are applicable to after a finite number of iterations. So exactly what you said, let's say that there is some algorithm, it has to run for 10,000 iterations. And after that 10,000 iterations, the effect of the network, it goes away. So within that 10,000, you'll have that agreement. Sometimes you can show that the rate at which the network agrees, the agreement happens is faster than the rate at which they all converge. So we have shown, for instance, another variation that agreement happens at 1/k square, but then optimality happens at 1/k. So, but this is still more asymptotic because there is no finite time in a way, right? So you know that one will converge faster than then. So these are the type of arguments right? Does it make sense?
Yeah, it does. Well, thank you so much. We'll conclude here with another round of applause as an appreciation. And
thank you, Usman.
Thank you, Frederick.
This
Thanks, Mert.
Thanks,
This
Usman.
concludes our seminar.